Thanks, Anthony. Couple of things to say. First thing, I should also join the choir in saying this is my favorite conference, and it really is. It's also literally, I mean, let's see, maybe the only conference I'm going to this year. That's the first thing to say. Second thing, I have the slightly thankless task of having amazing co-authors that are way better presenters than me. So I hope you will bear with me. And let me just go forward to where I'm supposed to start talking. All right. So this is actually kind of the project that first came to our heads, and then we started the whole well-based thing. We only really made it initially to write this paper. And what this paper is about is essentially another reaction to a paper that many of you will be familiar with, published by Bond and Lang in the Journal of Political Economy, where they essentially made the claim that our field is crazy and can't, produce any sorts of reliable results because of the way well-being is being reported on these discrete and ordinal scales. And what this paper is trying to do is using this well-base to assess this kind of claim, to check, okay, how easy is it actually to reverse kind of coefficients and a couple of other things like statistical significance and marginal rates of substitution. And so that's what we're using this well-base for in the first instance. So in this presentation, I will go through sort of 4 things. The first one is just to give some methodological background as to where those kinds of reversals can come from and how we can test for their ease of occurrence. Then I will give a little demo of a new stata command, which should make it really easy for you to, when you run your own regression, to check for the ease of reversals in your own kind of work. And then I will give some results based on well-base, and then I will close with some things that we're planning to do in the future, and we would like to get some feedback on those. Okay, so let's start with some methodological background. So what do we normally do? Normally what we do is, well, we take responses to some well-being question. For example, how satisfied are you with your life? All things considered. We all know this question. And then we take the responses and label them in some way. And normally what we do, we label them in their rank order, right? We give a 1 to the first response option, we give a 2 to the second response option, and so on, up to some largest kth response option that we label with the number k. And then we take a bunch of covariates, call them x, and then we run a regression. Normally an all-S regression, but sometimes, you might have an instrumental variables approach. Sometimes you might have fixed effects. You might have random effects. It all applies to those kinds of regressions too. The problem also applies to, say, you run an ordered probit or an ordered logit. It's a bit more complicated in those cases, but the same problem arises in those kinds of regressions too. So that's normally what we do. Now, when we do this, we essentially make 2 key assumptions here, and I will mostly focus on the first assumption. And this first assumption is, well, we need linearity. And one way of cashing this out, I mean, this is possibly a bit too complicated of a way of explaining it, but let me try. So what we have are these responses R to a question on well-being. And we hope that they're in some way related to an underlying kind of mental state that is in some way important. And we here call this underlying mental state H for happiness. And then what the linearity assumption essentially states is that the differences across response categories, for example, response category K and response category K-1 is always constant. So for any 2 kinds of response categories, you always get the same differences. When you move from a 2 to a 3, it changes your happiness by the same amount as moving from, let's say, a 4 to a 5. And that will be true across all kinds of response categories. That's roughly the first assumption, this linearity assumption, which I will be focusing on. And the second assumption, what we call a homogeneity assumption, is kind of a sort of a special case of the comparability assumption. Essentially what this says is that if a set of people is in a given response category, let's say the 3rd response category, then their mean underlying level of, in this case, happiness will be the same as any other group of people that also reports this particular level of well-being. So for example, if let's say we ask all the economists in this room, how satisfied are you with your life? And we take the people who say 4. Then we take all the sociologists in this room. We ask them how satisfied you are with your life. We take only those people that say 4. Then we require that their mean underlying level of happiness is the same across those two kinds of groups. That's roughly what the homogeneity assumption states. And essentially, the problem with this is that once we drop those kinds of assumptions, we can get into terrible, terrible troubles. I kind of covered this, so I will keep going. So first of all, with respect to linearity, essentially what we can do, and a version of this was initially shown in Bond and Lang's paper, and then I had a version of this for the case of OLS regressions in particular, which is kind of weaker. And essentially what the idea here is that suppose we have our standard regression coefficient beta, which comes from an estimation from a regression of our standard responses, Ri, on a bunch of covariates, Xi. And then what we can do is we can create this new kind of variable, Di, which essentially just dichotomizes our original scale at every level. So we create a new binary variable. Let's call this variable for the case of response category 2. So then we assign people a level of 1 if they fall below the response category 2, and otherwise we give them a 0. Now we can do the same thing with response category 3. So we label them with a 1 if they fall below a 3, and we give them a 0 if they fall above it. And then what we can do is run regressions of all of these new binary variables, and we get a new bunch of coefficient estimates. And it turns out that this bunch of new coefficient estimates is very closely related to our original beta coefficient. And in particular, what we can show is that if we run these regressions of these binary variables, and we always get the same coefficient sign, then it will be true that even if we drop the linearity assumption, if we completely drop it, we still will always get the same coefficient sign, no matter how we label our dependent variable. But if this sort of test does not hold true, then it will be the case that we can always reverse our coefficients. There will always exist some transformation of our dependent variable, so our reported happiness, that will yield a reversal of coefficient signs. So that's really quite problematic. And it's sort of a version of the Bond and Lang critique for the special case of OLS regressions. I would skip the bits on homogeneity, but there's a similar version of that in there. Okay. So, but what we were thinking was, well, we don't normally just care about the sign of a regression coefficient. I mean, that's one thing, but we often also care about two other things. The first one is false positive and false negatives. Like, are our tests of statistical significance affected by these sort of relabeling of the response categories? And the second one are, I mean, we talked about this quite a lot this morning, are marginal rates of substitutions. So are the ratios of coefficients that we get from our regressions affected by relabeling the response categories? And it turns out that we can say some useful things about that too. So first of all, what we can show is that if in our initial test, we found that the original coefficient was in fact reversible, then the p-value associated with that coefficient can essentially be anything between, this shouldn't be 0, this should actually be this expression here, and 1. And when the coefficient is not reversible, so we always should get the same sign no matter how we label the response categories, then it will still be true that the p-value associated with this coefficient will have to fall within the range of the p-values that we obtain from the regressions of these binary variables that we've generated. So what that means is that in the case where a coefficient is not reversible, we can actually bound the p-value associated with that coefficient even after giving up the linearity assumption, which seems kind of useful. And a very similar result holds with respect to marginal rates of substitution. So when the denominator in a marginal rate of substitution is reversible, then it will turn out to be true that you can essentially get any marginal rate of substitution that you want. It will essentially be bounded, I mean, unbounded between minus infinity and infinity, and we're kind of in hell then. But if that coefficient is not reversible, then we have, again, the same kind of result that the coefficient ratio will be bounded by these coefficient ratios of the associated regressions of the binary variables. So that's, again, kind of useful. At least we can give a bound on the marginal rate of substitution. So that's nice. Okay, so far I've only said that, okay, these kinds of bounds exist. Sometimes reversibility is possible, but I didn't really say anything about how we should sort of label the response categories in order to actually achieve a reversal or to achieve a change in the level of statistical significance or to achieve a change in a given marginal rate of substitution. And one thing that we kind of want here is to find that kind of transformation, so that set of labels that would in a certain sense be the least nonlinear to get sort of, let's say, a reversal of a coefficient. So can I label the response categories in a certain way such that, for example, I get a coefficient, a reversal in the sign of a coefficient, but that leaves sort of the response scale as linear as possible. And that's one way of doing this. Specifically, what we do here is we sort of think about it as a cost, where the cost is greater the more non-linear our resulting scale is. So just to make this a little bit more precise, so let Lk and L tilde k be the labels we assign to the kth response category, where the one without the tilde is the original response scale, which is normally labeled 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then L tilde k is, our transformation, where it might be, for example, I don't know, 1, 2, 4, 8, and then 9, 9.5, 9.9, 9.995, and so on. Okay? And now what we do is we try to minimize this cost function that sort of tries to track the nonlinearity in our transformation. And one specifically useful cost function is to say, okay, let's minimize the sum of the second differences, which is roughly to say, okay, so in a continuous context, it would be sort of, let's minimize the total, the integral over the second derivative, because the second derivative in a way gives us the nonlinearity. So if we minimize the integral over the second derivatives, that should give us a measure of the degree of nonlinearity. And that just reproduces this here in the discrete context. And then this sort of gnarly expression at the front essentially just normalizes this cost to fall between somewhere between 0 and 1, such that we can have it comparable across different types of scales and can sort of compare across different kinds of studies. And then we have this bunch of constraints. I don't think I will get into sort of the details of those kinds of constraints, but I'm happy to talk about them in more detail. But it turns out that when you set those constraints, then you can minimize this cost function and find that transformation that, for example, yields a coefficient reversal, but also yields a scale that is as linear as possible while still achieving that goal. Of course, other cost functions are possible, but then the results are pretty similar. Okay. Now I realize that this stuff is fairly complicated. I don't know how many in the room I've lost, and it's completely fine to be lost at this point, because we now have a stata command, which I think is kind of nice. So let me just demo this stata command quickly. So the idea is, well, first of all, what you should do is run your standard well-being regression. So here, I literally did this morning. I just took a bunch of data from the GSS and just went, let's go reg, happy, age, gender, employment status, and whether you have kids. I mean, some random regression. And you get, your results, your coefficients. And then you're wondering, which of those coefficients is actually reversible and at what cost are they reversible. So now what you can do is you can write RR utility with a bunch of options that I explained in a help file. And what it will do is essentially give you which of those coefficients are in fact reversible and at what cost are they reversible. It will give you the original p-value and then also the maximum and the minimum p-value. So you can check for any of your results, hey, how robust are actually my results against this kind of problem? And it should be fairly easy to run. The whole thing works with, suppose you have fixed effects, suppose you use random effects, suppose you have an IV regression, suppose you use weights, any of those kinds of options are supported by that command. So it should be fairly easy to use. So that's kind of useful. What we can also do is run the second kind of command that we have, which gives you marginal rates of substitution. So essentially what all you have to do is say, well, I want to know the marginal rate of substitution between, for example, having kids and being unemployed. And what it will output is, first of all, the marginal rate of substitution in the original case, and then the min and the max. So the maximum marginal rate of substitution and the minimal marginal rate of substitution between the two variables that you specify. But it will also produce a nice graph for you to show you how much the marginal rate of substitution changes as you allow the cost, so the degree of nonlinearity, to increase up to some maximum and down to some minimum. So that's, I think, kind of useful because now it's fairly easy for pretty much anyone to check your results against those kinds of concerns. How am I on time? All right. Cool. So this is all methods talk, but I guess we are also here for more results on the well base. So what we can do, and all of those results were produced using this particular stata command. We can check a bunch of things. We can check how likely are actually reversals in the database of coefficients that we have. How easy is it to change statistical significance? We can look at marginal rates of substitution, and we can also predict the ease of reversibility, but I'm not going to cover this today. Okay, so first of all, how likely are reversals across all the published estimates? Well, it doesn't look too great. So roughly speaking, in principle, reversible are roughly 60% of all results out there. Now, what that means is there exists some transformation that would give you a reversal of the original coefficient. But in many of those cases, the transformation that you require will be a fairly sort of implausible one. So for example, one where there are no differences between response categories 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then from 10 to 11, you get a massive difference. So this would, for example, be an implausible kind of transformation. What we think currently, but we have no good estimate, is that a cost of somewhere between 0.1 and 0.2 still is plausible, and higher costs are really no longer plausible. So if you think of it that way, then it will actually be the case that it's more like 20 to 30% of all results that are actually plausibly reversible. But still, maybe not ideal. The good thing, though, is that if we split the sample between estimates that are originally statistically significant and those that aren't originally statistically significant, then it turns out that even under the most kind of extreme circumstances, only roughly 30% of results are reversible at all. So this is really rather good news, that if you have a statistically significant coefficient, it's fairly unlikely to be reversible. So that's kind of nice. Okay. It still seems, overall not ideal. So the question is sort of the well-being research or life satisfaction research in this case kind of unique in this, or are other fields having the same problem? So what we did is we just went to the top 5 economics papers. So, AER, QJE, and so on, and just searched for, the term Likert scale and took all those kinds of published results. And most of them were sort of stuff on trust, productivity, risk preferences, and those kinds of things. And then we checked, well, among those kinds of results, which are using Likert scales, but which aren't well-being related, how easy are reversals there? And it turns out the problem is even bigger for the other people. So that's kind of nice in some way and maybe terrible in another way. So in those kinds of cases, it's actually 80% of all results that are reversible. So that's sort of good news. Well, how likely are then changes in statistical significance? So it turns out that of the, in this case, 12,000 estimates that were initially statistically significant, it is possible to make them insignificant by some transformation of the dependent variable in roughly 70% of cases. We haven't yet checked how this actually varies across our cost, but it seems fairly easy to do that, to make a statistically significant result ultimately statistically insignificant. Roughly similar number in the case of type 2 errors. So you have an initially insignificant result and you try to make it significant, then in more than half of cases, that's also possible. Okay, final bit then on marginal rates of substitution. So Anthony already talked about sort of marginal rates of substitution between income and unemployment. So what we have here is a large number of papers that give either estimates of income or of unemployment. But there's a smaller subset of papers that have both of these things at the same time and that yield coefficients that are non-reversible in their estimates. So we only took the subset of studies that met those two kinds of conditions, which were 5 papers, and found an initial mean marginal rate of substitution of 3.3 there between the log of income and being unemployed. Okay, so the question is, how easy is it to change this marginal rate of substitution? And it turns out, well, you can get sort of wide bands here, right? If we start at a marginal rate of substitution of 3.3, we can, with some extreme transformation, push this up to sort of a marginal rate of substitution of somewhere around 10, slightly less than 10. So that seems fairly extreme here. But of course, it also turns out to be the case that if you draw the line for each individual paper, you get fairly strongly varying sets of marginal rates of substitutions across papers. So this is sort of a separate concern, right? It's not a methodological one. It's more one about, okay, different studies get different results, but it sort of shows sort of the importance of this particular problem. Now, what we can also do is check how this varies across panel studies and how it varies across purely cross-sectional studies. And there it turns out that, first of all, the marginal rate of substitution is much higher in the panel case overall, but that it is also much more sensitive to relabeling the dependent variable. Slightly unclear why that is, but here's just the result on that. Okay, let me skip the next steps. Maybe we get to this in the Q&A and just summarize very quickly. It turns out sign reversals are a problem, but they're less of a problem if you already have a statistically significant result. Significance is a fairly big problem in the sense that we can very often make a significant result insignificant, and marginal rates of substitution can really vary wildly, almost by orders of magnitude. And so that really is a problem, especially, for example, if we want to implement sort of Kuhn's proposal, then we have a bit of a problem, but I think it's solvable. And I will end there.
Do we have to understand the math to use your static code?
No, it helps.
I'm kidding, of course. Questions? Looks like Chris was. Oh.
Very quickly, just curious about the Likert scales. Can you tell us a little bit more which ones you tested? Was it on the same papers that were selected for the well-base?
No. So in this case, it was like, take the top 5, search for, do they ever mention Likert scales? Take everything that's out there, get the papers that have a Likert scale as a dependent variable, and then use those papers to then do these estimations.
The Bayesian sees this and desperately wants to have a distribution of beliefs rather than focusing on dichotomous reversals and bounds. So is it possible to assign probabilities to the costs, for instance, maybe on the kind of stuff that Mark has done by asking people, so that would be empirical or something else? And if so, then one could just actually get a revised distribution of beliefs for a coefficient.
Basically, my question was covered already. I wanted to know the dependent variable, in which scales did you test it? But Likert scale, I suppose, 0 to 10 or 1 to 10.
Okay, let me take this in reverse order. So here it's literally any, right? It moves, sometimes you only get 3 response categories like in the GSS, and it moves up to 11 response options. But the problem is general, like people started to use sort of visual analog scales where you have 1,000 response options and you get the same problem. Now, with respect to the okay, we need some estimate of the costs. And that really is our next step. What we want to do is run a survey and get an empirical estimate of what plausible values for the cost are. We have 2 kinds of methods that we're thinking of. One is to literally just prompt people to say, oh, here's a response scale. Please use it linearly, and compare that to the results we get when we don't prompt people to use the response scale linearly, and see if it makes a difference. And the extent to which it makes a difference can be then sort of translated into a cost. There's a way of doing this. So that's one way. Another way is to roughly use something like calibration questions. Like you could, for example, literally ask sort of Benjamin et al.'s types of calibration questions. But what you can also do is sort of ask people, oh, how tall are you? Give the actual number, like, I don't know, 1.80 meters. And then on a scale from 0 to 10, how tall are you? And you can do this with lots of types of questions. You can do this with height, you can do it with weight, you can do it with your income, you can do it with the size of your house, and so on. And then you can sort of test whether the cardinal value of your actual height is linear in your subjective response to, oh, on a scale from 0 to 10, I'm like a 7 in terms of my height. And you can then relate sort of linearity in the subjective question to the actual underlying cardinal level. So those are the 2 methods we're currently thinking of in order to get at the cost. But if you can think of something better, we would love to hear it.